I've been diving deep into GTA 5 recently, and I was shocked by how bad the underwater scenery looked. Alright, I know, the game was released in 2013. Surely newer AAA titles have made this like 10 times better, right? Well, nope. Just look at this. An empty underwater scenery with an extremely small number of fish on the screen, and I don't even want to comment on this from AC Valhalla. And just when I started to lose hope, I stumbled upon this indie masterpiece. Fish swim like they're alive, they form schools, and the whole world feels rich and organic. So it can be done, but since this game is only about underwater exploration, is the fish simulation so expensive that it can be included in AAA games? This seemed a bit fishy to me, so I decided to stop guessing and build it myself. In this video, I'm taking you underwater in Unity. I will try to build a fish simulation system that actually feels alive and runs smoothly. Let's see if the big studios are slacking or if I've just bitten off more than I can chew. The things that almost every game got kinda right were the water and the environment. They aren't the main focus of this video, but I need them to showcase the fish. So I put my modeling skills to the test and created some 3D models for the environment. Then I added a simple terrain and placed some grass and corals on the surface. Next, I added some rocks to form a closed area, and finally, I added a water surface and some post-processing effects to create the illusion of an underwater experience. With that out of the way, I was ready to start working on the fish. But before I do that, let's just take a look at the current performance of the scene. Alright, it's taking about 3.5 to 4 milliseconds to render each frame, which is about 250 frames per second. This will be my performance benchmark for comparison later on. Now, I was finally ready to begin working on the fish. I imported this little fella, which will serve as a guinea pig during my explorations. The first thing upon which everything else is built is to make sure that his swimming motion looks realistic. Usually, when you want to create a motion for the character, you would create a skeletal rig and animate the movement in a desired way, then save it as an animation which you would play at runtime. However, there's an issue with this approach. You see, skeletal animation is fine when you have one or a couple of characters, but in this case, I want to have hundreds or even thousands of fish, and this approach would completely crash the performance of the game. I need to think of a different way to animate the fish. While exploring the internet for answers, I found this video from the actual developers of Abzu. I couldn't believe my luck. Here, they were talking about this very issue. Their approach was to recreate a realistic fish swimming motion in the vertex shader by combining several simple motions. They created the game in Unreal Engine and didn't provide the source code, but their explanation and idea were more than enough to get me started. I created a new URP lit shader and injected this custom function inside the vertex shader. All that this function does is apply an offset to the local position of the vertex and return the modified position. The first part of the motion is the side-to-side movement. This is really easy to accomplish. I can just offset the x-coordinate of the local position of the vertex, and if the offset is guided by time and plugged into some sine function, I get something like this. Now, this is pretty cool and all, but this isn't how the fish swimming cycle looks. The second motion I've added is the yaw rotation around the pivot of the fish. Again, the code for this motion is very simple. I simply rotate each vertex around the y-axis that passes through the pivot. And here's the result. If I now combine both motions, we get something like this. Wait, this doesn't seem right. The problem was in the order in which the motions were applied to the vertex. I need to apply the rotation before the side-to-side offset. Otherwise, the result is incorrect. Okay, now it's looking better, but it still doesn't look good in motion. Yikes! Let's continue. The third motion is the roll rotation along the spine. And you may be thinking, in what universe do fish swim like this? However, the trick is to offset the rotation based on the vertex distance from the pivot to get this funky, gooey motion. This motion really provides that organic feel to the whole animation. And again, if I combine all motions together, we get the fully realistic fish swimming motion. Well, not yet, but we're getting there. The final motion I've added is another yaw rotation around the pivot, but this time It's offset the same way as the roll rotation. The result is a motion that resembles a flag moving in the wind. However, if I now combine it with all other motions, we end up with this. Oh my god, this looks so good. The movement is fluid and due to the roll rotation, it feels so organic and alive. Also, since it's implemented in a shader, I can just apply it to different type of fish and the movement will still look pretty good. Now, the fish swimming motion looks good, but I need a way to control how fast and intense the swimming motion should be based on the current movement of the fish. If the fish accelerates really fast, the swimming should be fast and dynamic to realistically support it. I have a feeling that this can become really complex really quickly, so I wanted to start with something simple. I implemented a very basic controller that maintains the desired movement speed of the fish. Essentially, the speed is constantly decreasing due to water friction, so the script maintains a steady acceleration that compensates for this velocity loss. Also, when I press and hold the left mouse button, the acceleration suddenly increases. Then, based on the current velocity of the fish, I update the intensity of the swim motion in the shader. Let's see how this is looking. When the fish is moving at a constant speed, it looks pretty good. However, as soon as I start increasing the speed, the movement seems slightly off. This is interesting. It turns out that the current velocity of the fish shouldn't guide the swimming motion. Instead, it should be controlled by its acceleration. This small change really made a huge difference. Look at it zooming through the water. Awesome. Motivated by this progress, I expanded the controller to support steering with the W, A, S, and D keys. Basically, the keyboard input updates the desired movement direction of the fish. Then, based on the angle between the current movement direction and the desired one, I calculate the required angular acceleration and velocity to tackle this angle difference. Let's have a look at how the movement is looking now. Like before, if I start accelerating, the swimming motion supports the movement really well. And when I start changing direction, it still holds up really well. I mean, at least when I accelerate and change direction at the same time. If I only try to change direction, the illusion of realistic movement suddenly breaks. This is not looking good. I have to say, I spent a few hours thinking about how to approach this problem. And then it hit me. When the fish starts to turn, it needs to start twisting its body and moving the tail fin, which should also result in some increase in movement acceleration. So, in other words, a percentage of angular acceleration should be reflected in the movement acceleration as well. Finally, I need to ensure that the angular acceleration also affects the intensity of the swimming motion, so I use the maximum of the current movement and angular intensity as a guide for the swimming motion. And here's the result. The fish swimming looks really convincing. When I try to rotate, the fish movement intensifies and the speed of the fish increases a bit as a result. I think I'm satisfied with the swimming motion when I control the fish, but in most games, the player isn't controlling the fish, it's simply sharing the environment with them. The fish should move on their own. For this, I implemented a simple test case where the fish always tries to move toward a certain target. Once it reaches it, the target is repositioned to a different location and the whole process is repeated. To implement this, I reused the movement code from the third-person controller and integrated it into an autonomous movement controller. Basically, the only difference between them is that the desired movement direction isn't being specified via keyboard, but is determined based on the position of the target that the fish is trying to reach. And this is how it looks in action. The fish swims at its normal speed until it reaches the target. Then it attempts to steer as quickly as possible toward the next target and moves directly toward it in a straight line. You can see how the swimming motion intensifies as the fish tries to rotate. This is starting to look really good, so I've expanded the test case with obstacles that the fish needs to avoid. When the fish enters the obstacle radius, it should accelerate to turn away from it as fast as possible. Also, I've added a couple of different animators for the target. One moves it in a straight line, the second moves it in a circle, and the third moves it in a squared-like pattern. With that, let's see how the simulation is looking. As before, the fish is swimming toward the target. And since the target is moving, the fish is actually following it around the environment. Now, if the fish encounters an obstacle on its way, it will try to move as fast as possible away from it, and then return to following the target when it's out of the danger zone. Okay, this completes the movement for one fish. This was challenging on its own, but I think expanding the simulation to multiple fish will be the more challenging part. I researched the behavior of fish schools and discovered that their behavior is remarkably similar to that of flocks of birds. This topic has been fairly well researched in computer graphics, with papers dating back to 1986. It's so common that there is a general term for the group of objects that follow movement patterns that resemble those of fish or birds. They're called birdoid objects, or Boids for short. And here's a fun fact. Boids simulation was used in Tim Burton's film Batman Returns from 1992. To summarize the papers, Boid movement patterns can be achieved by implementing three core types of motion. The first one is a motion related to Boids trying to avoid collisions with each other and maintain their own personal space. This type of motion is called separation. The next motion relates to keeping the same movement direction as the Boids around them. This motion is called alignment. Finally, the third motion is related to Boids trying to keep together and move as a cohesive unit. This type of motion is appropriately referred to as cohesion. By implementing all three motions, we end up with a behavior that resembles that of birds or fish. And here's how I implemented that. On every update of the simulation, each Boid checks the movement direction and position of all other Boids. Then, to maintain cohesion, it should move towards the center of the school, while to maintain separation, it should move away from the closest Boid next to it. Of course, it tries to align itself with other Boids by trying to move in the same direction as the average direction of all Boids. Finally, the resulting desired movement direction equals the sum of all those individual directions. However, there are different kinds of fish species out there. Some fish prefer to be closer together, while others are more individualistic and prefer to maintain their distance. I want to support all, so I exposed these multipliers that increase the weight of each motion so that I could tweak them from the editor. Finally, I've incorporated movements toward the desired target into the equation and made sure that the Boids remain within the simulation bounds. Actually, there's one more thing left to do. I need to determine the initial position of each Boid at the start of the simulation. Well, let's just use the random position and rotation for each Boid and see how that will look. Well, the fish are initially distributed across the whole simulation area, which doesn't really seem natural. But after a while, they're getting closer and starting to move in a pattern that resembles a school of fish. Of course, they're trying to reach the specified target while staying aligned with the rest of the school. They're forming a cohesive unit while still maintaining a safe distance from each other. Of course, we can tweak the behavior by adjusting the weights of the simulation. For example, let's see how a school of introvert fish would look by increasing the separation weight. That's really interesting, but the initial positioning of the fish is starting to bother me a bit. Since we know that the fish will try to move as a cohesive unit during the simulation, let's make them a cohesive unit right from the start. For that, I've changed the initialization logic to spawn all Boids equally distant from each other inside a sphere. This already looks much better, but let's remember the goal of this whole experiment. I'm trying to make the underwater environment feel organic and teeming with life. And while the movement feels realistic, let's be honest, this is just one small group of 20 fish swimming in the ocean. In real life, if you go diving at a coral reef, the ocean is teeming with diverse species of fish, and each species comprises hundreds of individual fish at any location. So let's get a bit closer to that by adding more fish species to the simulation. I've added a golden trevally, a clownfish, and a yellowtail snapper. I've set up their swimming motions and added them to the simulation. Then I've expanded the Boid behavior logic to update cohesion and alignment only to the fish of the same species. Finally, I've updated the separation logic to only check for the same fish species or the larger ones. This way, the smaller fish avoid the larger ones, but the larger ones don't care about the smaller ones. That's a bit better. However, it still feels extremely empty. Currently, there are approximately 100 fish in the simulation, and that is a rookie number. Let's try 300. Okay, this is starting to look better. Let's try 600 now. Well, it seems like my PC doesn't really like this idea. The performance dropped severely. If you remember from the beginning of the video, the benchmark with an empty environment took about 4 milliseconds to render the whole scene, which is about 250 FPS. However, with a total of 600 fish, the performance dropped to around 25 FPS or about 40 milliseconds per frame. Ouch! The issue is that every fish is checking every other fish for its type, position, and movement direction. With 600 fish, this comes to around 360,000 calculations each frame, and my CPU is definitely feeling it. Luckily, there's a relatively easy improvement that we can do to speed this up a bit. If we think about it, there is no need for a certain fish to do any calculations with a fish that is located far away from it. What really matters to each fish are its close neighbors. So, if we knew for each fish what its neighbors are, we could just skip over all other fish. Well, perfect, but how can we determine the neighbors in a performant way? A common approach for this kind of issue is to split the simulation area into multiple boxes or cells. Then, for each fish, we determine its cell based on its position inside the simulation area. Finally, after every fish is positioned in a corresponding cell, we can only check the fish in our cell and its neighboring cells instead of checking every other fish in the simulation. This kind of area split is usually referred to as a spatial partition of the area, and here's how I implemented it. I keep a dictionary of Boids located at each cell and another dictionary that maps the current cell ID for every Boid. With these two dictionaries, I can quickly fetch all Boids for a specific cell ID, but also quickly check which cell the Boid currently occupies. The ID of the cell is determined based on its size and the position of the Boid within the simulation area. Based on that ID, I can easily add or remove Boids from the dictionaries. And here's the visualization of these cells during the Boid simulation. The cells with the darker color are filled with more fish, while the transparent ones don't have any fish in them. And let's have a look at the effect of this optimization on the performance. Well, we're looking at about 20 milliseconds per frame or around 50 FPS, which is a speed up of almost 50%. It's nice, but not nearly enough. If I want to scale this further, I will need to think of a different approach. The main issue with the current approach is that the next fish in line can't start executing its movement update until the previous fish has completed theirs. This restriction is enforced because the current execution of the algorithm occurs on the main thread of the CPU. However, nothing is preventing other fish from executing their movement logic completely in parallel. And whenever you realize that this is the case, you should immediately consider porting your logic to the GPU, as it is the ideal tool for solving numerous independent logical tasks. So, if I transfer the simulation logic to the GPU, it should yield a significant performance boost due to the parallel execution logic. Without further ado, I started transferring everything to the GPU. First, I created GPU-friendly data structures to transfer the data from the CPU to the GPU. Then, I implemented a compute shader that runs the entire simulation logic, updating direction, movement properties, the whole shebang. Next, I had to rewrite parts of the quaternion class for execution on the GPU. And finally, I expanded the C# scripts to contain the logic for dispatching the compute shader and retrieving the results. Whew, that was a lot of work. Let's just hope it was worth it. Well, it looks like it helped quite a bit. The current simulation of 600 Boids is running at about 90 frames per second or around 11 milliseconds per frame. Let's crank the number of fish to see how high we can go now. Well, it seems like the struggle starts again at around 3000 fish. Damn, I was hoping for more. Looking at the profiler, I'm losing a lot of time just fetching the results back to the CPU side. It would be ideal if I could simply dispatch the compute shader and instruct the GPU to use those results to render the fish, without needing to bring them back to the CPU side. Luckily, in my recent project about recreating the terrain scan mechanic from Death Stranding, I learned about indirect instance rendering, which basically allows issuing a single render command to render a specific mesh multiple times. What is cool about this is that I don't need to fetch the data back to the CPU in order to provide it for rendering, which sounds perfect for this use case. However, to support indirect instance rendering, I need to adjust the fish swimming shader slightly. First, I declare the required data structures and variables that will be used for rendering. Then, I expanded the vertex shader arguments with an additional ID that represents the index of the fish that is currently being rendered. With that ID, I can sample the Boids buffer at the correct index and retrieve the data about the Boid being rendered, including its position, rotation, movement speed, and so on. Then, using that data, I can render the Boid at the correct world position and with the correct rotation and swimming intensity. Let's see how the simulation is looking. Well, there's good news and bad news. The good news is that we've gained a bunch of performance with this. Our biggest bottleneck is solved. The bad news is that the fish are constantly flickering. I mean, what is this sorcery? After commenting out various parts of the compute shader and running the simulation repeatedly, I've pinpointed the issue. I've accidentally flipped the comparison sign in one of the functions inside the helper quaternion shader file I've written. Well, that's another couple of hours that went straight down the drain. With that out of the way, let's take a look at the performance again. Damn, my PC seems to be enjoying this new approach. It seems like it's not even breaking a sweat with 3000 fish on the screen. I gotta say, this is a huge relief. However, I'm not satisfied with 3000 fish. I need more. Let's push this to the limits. I've doubled the number of fish to 6000. Well, by looking at the stats, this hasn't impacted the performance at all. Wow, this is unbelievable, considering that previously increasing the fish count from 100 to 500 demolished our frame rate. But I'm not stopping here. Let's see how far we can push this. Okay, I can finally hear my PC starting to struggle with 30,000 fish. And by looking at the frame rate, we're sitting at around 50 FPS or approximately 20 milliseconds per frame. And let me tell you, I'm not sure what to think about this. 30,000 fish is a lot, especially due to the complex movement logic we're constantly running in order to get the realistic swimming motion, but it's eating away way too many frames, and in this state, it wouldn't be suitable for AAA games. Then it hit me. I was in this exact situation before on the CPU side. Even though the GPU is running all the fish in parallel, each fish is still calculating comparisons with every other fish in the simulation. What if I implemented the spatial partitioning logic on the GPU? And due to the way that the GPU works, will this even provide a performance boost? I guess there's only one way to find out. Let's revise the game plan. Once again, I will divide the simulation area into cells. Then, every frame, I will dispatch a compute shader that places each Boid into the corresponding cell based on its position within the simulation area. Finally, during the execution of the Boid simulation, each Boid will only need to simulate its behavior based on the Boids located in the neighboring cells. Now, before I press play, what do you think? How much performance are we going to get out of this? 10%? 20%? Pause the video and leave a comment with your prediction. Okay, here we go. Oh yeah, there we go. The 30,000 fish are being simulated at around 8 milliseconds per frame or about 120 frames per second. That's a speed up of almost 60%. There's probably more performance that can be squeezed out, but I think this is good enough for now since this seems like a bit too much fish for a realistic feel. To complete the scene, I've added a couple of sharks that will patrol the area and serve as obstacles that the fish will try to avoid at all costs. And this is the final result. A rich and colorful underwater scene full of life, with realistic fish swimming motion and school movement patterns. And the performance? Well, this rich scene is running at approximately 5 milliseconds per frame or about 200 FPS. I think this leaves plenty of room for other functionality and gameplay elements, proving that it can be done and that the AAA studios are just slacking and being lazy. What do you think? Have I overlooked anything that might affect the performance or missed something major that will make this feel more alive? Let me know in the comments below. Now there was one more thing I was dying to make, ever since I experienced playing Abzu. This behavior of a school of fish swimming in a circle to confuse predators. This is a natural phenomenon and happens in real life, and it's also a perfect test for my newly created Boids system. I quickly set up another underwater environment and added about 5,000 fish to the simulation. Also, I've added a single target to the center of the simulation area. My idea is that this target will attract fish towards the center, and then they'll try to avoid each other and hopefully form the famous spherical pattern, but let's see what will happen. Well, they're certainly going towards the center, but they're not really creating the desired formation. I feel like they're getting too close to one another, so let me try to add an obstacle that will cause them to start moving away from the target a bit sooner. Okay, this is starting to look a bit better, but there are a couple of issues. First, the obstacle is too small. I need to increase it a bit, and secondly, I don't really like waiting at the beginning of the simulation for all the fish to get to the center. To tackle this, I've expanded the initialization logic to spawn all fish on the surface of a sphere, uniformly distant from each other. If the sphere is of the same size as the obstacle that encapsulates the target, the fish should immediately start forming the desired movement pattern. But let's see this in action. Wow, this looks so cool, and they're immediately forming the desired movement formation. I've gotta say, I'm extremely pleased with how this turned out. And with that, I can finally mark this journey as completed. I've investigated the issue of bland and lifeless underwater experiences in games, and have hopefully demonstrated that with a little bit of effort, one can achieve a realistic and joyful underwater scene full of life. If you enjoyed this exploration and you'd like to support us, or just explore the project files and create your own underwater simulation, then our Patreon account is the right place for you. Your support keeps this channel alive, and we're incredibly grateful for it. And that's it. Good luck with your projects, and I'll see you in the next one.